Welcome to this proof of concept video. This video is part of a series about drawing dynamical portraits of modular arithmetic. In the video Modular Arithmetic in Motion, we introduced the notion of a dynamical portrait, showing addition or multiplication by one element of z mod nz. So here's an example on our intro screen here, the portrait of multiplying by 2 modulo 6. The arrows show what multiplying by 2 does to each element. In that video and its follow-up, we discovered some things about these portraits and what they might look like in general. We saw that additive dynamical portraits were very regular. They consisted of some number of cycles, all of the same size. We also discovered the number of such cycles. It was the GCD of A and N, so that's how many you have, and then necessarily the size has to be N, the total number of elements, divided by that size. We took a look at some multiplicative dynamics, and we saw that they were pretty kooky overall, doing all kinds of irregular looking things. And in particular, sometimes they were cycles, sometimes they were not cycles. We did prove one very important fundamental observation about dynamical portraits. And I should emphasize here that you could draw a dynamical portrait of any function on a finite set. If you have a function going from a finite set to itself, you can draw arrows to show how it acts. We just happen to be focusing our attention on the functions z goes to z plus a mod n and z goes to az mod n for some fixed a. The important result that we proved is this. Any dynamical portrait of a function is made up of cycles if and only if the function is bijective. Our goal for today is to say something about the shape of multiplicative portraits. We won't get as satisfyingly complete an answer as we did for the additive case, but we can investigate some of what's going on. If you're in my class, then in between these two videos, we did some worksheets to discover the answer to this question by exploration, conjecture, and proof. And I encourage everyone to check the links in the description to access these. This video can serve as a sort of summary of that exploration, or it can stand on its own. Okay, let's jump into some examples. Here's the multiplicative dynamics of multiplication by 1. It's kind of silly to multiply by 1 because you don't change anything. So that looks like a single loop at every point. It's worth noting, though, that this function is invertible. It is bijective. In fact, it has an inverse, which is itself. That is, if you do nothing, you undo it by doing nothing again. And as promised, the dynamics does consist of cycles. Lots and lots of tiny one-element cycles. Okay, next up, multiplication by 2. Already, things are a mess. Just look at this. Mod 3, we get cycles, but they vary in size. So we've got 1 cycle and 1 2 cycle. Mod 4, we have 1, 2, and 3 kind of feeding into a 1 cycle at 0. And modulo 8, well, actually, the thing to do here might be to unfold it a bit. Everything is feeding into 0 like a tree. Let's try a few other pictures of multiplication by 2. Mod 5, 0 seems always to be on its own little loop. I guess that makes sense because 0 times anything is 0 again. So that's going to happen in all of these pictures. Mod 5, it's alone and everything else forms one big cycle. Mod 6, we have some feeders again. So 3 feeds into this little 1 cycle at 0, while 1 and 5 feed into a 2 cycle alternating between 2 and 4. Mod 7, we have cycles again. 0's alone and the rest fall into 2 cycles of the same size. Mod 8, we have this great tree pattern that we saw a moment ago. Mod 9, we have cycles again. 0's alone, and then we have cycles of size 2 and 6. So, obviously there's quite a lot going on here. Let's point out a few intriguing things. First, when is it all cycles? Remember, this is the same as asking when the function is bijective. So taking a look at this data, it looks like it happens for the odd moduli. So, conjecture. The dynamical portrait of multiplication by 2 consists of cycles if and only if the modulus is odd. All right. Using the relationship to bijectivity, we could actually rephrase this in terms of bijectivity. So the function z goes to 2z is bijective if and only if the modulus is odd. Okay. Let's notice some other intriguing things, though, while we're here. So when things aren't cycles, it's interesting that the in arrows seem to come in pairs if they come at all. Take a look at mod 6. 0, 2, and 4 all have 2 in arrows, whereas 1, 3, and 5 all have none. The same kind of pattern either 0 or 2 in arrows, seems to hold on all of the even modulus pictures. The next thing I notice is that the picture mod 6 looks like the picture mod 3, but with some extra feeders at every point. So I'm using this word feeders informally to mean arrows that come in and aren't part of the cycle themselves. So actually the picture mod 4 and mod 8 are similar too. You might notice some other interesting observations. In fact, I encourage you to pause the video here and see if you can identify any other interesting patterns. Chat with your peers and make some conjectures. Okay, well, there are a ton of patterns to notice here, but I'd say that these observations aren't enough to make a conjecture yet. I encourage you to experiment and make your own conjectures. Following the links below, you'll actually find an online tool that will draw dynamical portraits for you so that you can quickly take a look at a lot of data. For this video, I want to focus just on the question of when these pictures have cycles and when they don't. So we just observed that for multiplication by 2, it seems to be that we get all cycles when the modulus is odd. Let's try a different perspective now. So let's try varying the a, the thing we're multiplying by, instead of the modulus. Here we were fixing a to be 2 and looking at different moduli. So instead, let's fix one modulus. As a number theorist, I like to pick 12 because it's handy size and its factorization has a good mix of stuff. So the prime 2 is repeated and 3 is alone. So let's look at various multiplications mod 12. All right. Multiplying by 1 is kind of boring. Everything goes to itself, but it is an example of a portrait made entirely of cycles, just 1 cycles. Multiplication by 2 has this tree thing happening with feeders heading into a single 1 cycle and a 2 cycle. Multiplication by 3 is similar, so feeders into some smaller cycles. Multiplication by 4 has triple feeders, so 3 things heading into each. That's kind of cool. Multiplication by 5 is all cycles. So we found another one here. So we've got 4 1 cycles and 4 2 cycles. So how can I tell which are 1 cycles and which are 2 cycles? Kind of looks like the multiples of 3 are important. Interesting. Multiplication by 6 is pretty wacky. Okay, in fact, 0 and 6 both have 6 in arrows each, and then one of them just points to the other one. If I thought I understood things, I'm not as sure anymore. Multiplication by 7 now has 6 1 cycles and 3 2 cycles. Looks like the even numbers get the 1 cycles in this case. Okay, so this is certainly fascinating. There's way too much to consider here. So let's just focus on the one question. When do we get just cycles? So in this zoo that we have on the screen here, we get a portrait made entirely of cycles for 1, multiplication by 1, multiplication by 5, and multiplication by 7. So what's special about those? Well, you might have guessed it, having been primed from other videos to think about GCDs. Take a moment, pause the video, and make a conjecture. Okay, here's the conjecture that I made. Conjecture. The portrait consists of cycles if and only if A is coprime to N. Did you make the same guess? So this guess actually works for the multiplication by 2 data we collected earlier as well. There it was exactly the odd moduli that had all cycles. So let's just go for it and draw the rest of the mod 12 pictures to verify our conjecture. Okay, multiplication by 8, not all cycles. By 9, not all cycles. By 10, not all cycles. By 11, all cycles. So it looks like our conjecture could be true. The only A coprime to 12 on the screen right now is 11, and that's the only one with cycles. Before we get to proving it, I want to draw your attention to one more aspect of these pictures. It's a sort of arithmetic consequence of the pictures that will be important. Okay, here's the issue. You might have an equation, mod 12, that you want to solve. Suppose we've got 3x is congruent to 6 mod 12. So looking at this, let's actually rewrite it slightly so that the 6 becomes 3 times 2. You are mightily tempted to cancel the 3's, aren't you? You would get x is congruent to 2 mod 12. That seems reasonable. After all, 2 certainly is a solution to the original equation. Just plug it in. 3 times 2 does come out to 6 mod 12. But before we get too proud of ourselves, let's solve this with a dynamical portrait. So which portrait do we need? Well, our equation is looking for something which when multiplied by 3 gives 6. So let's look at multiplication by 3 mod 12. Which things give 6? Now from the perspective of this picture, the question is asking us to find the elements whose arrows point to 6. That is all the things which when multiplied by 3 become 6. So look, there are 3 of them, and we were so sure the answer was just 2. In fact, another answer is 10 because 10 maps to 6. Let's verify that, right? 10 times 3 is 30, which simplifies to 6 mod 12 when you take away 2 copies of 12. But wait, I said 3 of them. We've also got 6 mapping to itself. So 3 times 6 is 18, which also simplifies to 6 mod 12. So this problem actually has 3 solutions, 2, 6, and 12. Okay, so here's a quick self-test. Here are a bunch of dynamics mod 12 again. Use the picture to solve the equation 6x congruent to 6 mod 12. Go ahead and pause the video. Okay, I looked at the dynamics of multiplication by 6. I got 1, 3, 5, 7, 9, and 11 as my solutions. So I definitely can't just cancel the 6 and get x congruent to 1 mod 12. There are in fact a ton of solutions. So this question of when you can or can't cancel something mod n is very important, and it's actually closely related to the question of which pictures consist of cycles. So after all, the obstruction to canceling seems to be when we have these feeders or multiple arrows heading into the same place. So it appears at least that canceling fails when we're in the not all cycles case. So actually the best way to think about this might be to go back to the language of functions. What does it mean that there are multiple arrows pointing into one element? So in terms of functions, this is a failure of injectivity. The function is not injected. So for a quick review, here's the definition of injectivity for a function. So injectivity is when f of x1 being equal to f of x2 actually implies that x1 had to equal x2. So in other words, the same output means that you had the same input. No two different inputs can give the same output. So in order to make the connection, we've always been talking here when we draw these pictures about the function f of x equals ax, which is multiplication by a. So if we're using this function, then the definition of injectivity becomes that if ax1 equals ax2, then x1 equals x2. So the definition of injectivity becomes we never have two arrows colliding at one element. So having the ability to cancel is actually the same as being injective. In our context, these are just the same thing. Okay, so we have a little bit of a chain here. So f is bijective if and only f is injective, if and only if cancellation is valid. That first if and only if between bijective and injective is actually a standard result from the theory of functions, which applies when you have a function from a finite set to itself. The second one is the one we were just talking about, that injectivity of the function is actually this notion of cancellation. But remember, our conjecture that we were what we were aiming at was to get to the statement that a and n are coprime. So for this, we'll have to look a little more closely at cancellation and see if we can make the connection to coprimality. So let's take a look at this. Here's an example of cancellation. So 5x congruent to 5 times 1 mod 12 implies that x is just 1 mod 12. So the GCD and coprimality is something about the divisibility relationship between integers. So let's rewrite the mod notation here in terms of divisibility to take a closer look at this cancellation fact. So that fact we had on the screen is logically equivalent to the following, which is that if 12 divides the difference between 5x and 5 times 1, then 12 divides the difference between x and 1. So let's actually factor a little bit and rewrite this again with something logically equivalent. This is 12 divides 5 times x minus 1. Implies that 12 divides x minus 1 itself. Okay, so look at that. Think about the relationship between 12 and 5. If 12 divides 5 times this thing, where can that 12 live inside 5 times this thing? It can't it doesn't share anything with the 5, so it has to live entirely inside the x minus 1. So actually, this is a consequence of the fact that 5 and 12 are coprime. So this cancellation is allowed, and the way to see that it is allowed is because of the coprimality. Okay, so for this observation above, notice that I put the x and 1 together and thought of x minus 1 just as a thing. I didn't really need to look at the guts of the thing. It was just some number. So let me move to a slightly more general situation and replace the 1 with a y everywhere in what we were just talking about. Everything we said is fine there. So then our condition here at the end is that 12 divides 5 times this thing implies that 12 divides the thing itself. But there's no reason for using the two variables there, right? They only appear in the related quantity x minus y. They don't appear on their own. So as x and y vary over all possible values, so does x minus y. And that's the only thing that actually matters. So the content of the statement is exactly the same, mathematically speaking, as if we replaced the x minus y just with a z. Okay, and that's great because it's simpler. All right, so we're going to make that sort of change. Okay, so now we really have the relationship. So this was an informal discussion of what's going on here, and we're going to have to do a formal proof. But we've got the general structure. We've got that f is bijective if and only if it's injective, if and only if cancellation is valid, and cancellation is valid if and only if a and n are coprime. We didn't actually prove all of this. We have to go into the details here to be sure that we've actually proven it. Let's write it out a little more carefully with a few more intervening steps to begin with. Okay, so the dynamics of z to az consists of cycles if and only if the function from z to az is bijective, if and only if it is injective, if and only if cancellation is valid, and here I've written out the mathematical formulation of this notion of cancellation being valid, which is that if ax is congruent to ay mod n, it implies that x is congruent to y mod n for every x and y. But what we just saw is that that is actually logically equivalent to the statement that if az is congruent to 0 mod n, then simply z is congruent to 0 mod n for all z. So we're replacing, here's that trick, replacing x minus y with z. Okay, and now let's rewrite that in terms of divisibility. So n divides az implies n divides z for all z, and now we can see how the coprimality comes into it, and we'll have to show that that's if and only if a and n are coprime. So we haven't actually proven every step of this, but we've sort of given the highlights and ideas. So now it's time to write out a careful, complete proof. Theorem. The dynamics of z maps to az consists entirely of cycles if and only if a and n are coprime. Okay, so let's remind ourselves of the game plan in the margin, okay, and I'll actually label them all. So the proof is going to be a whole sequence of equivalent statements, and I have to convince you that they're all equivalent from one end to the other. Okay, so proof. We will prove a series of equivalences. So these are the if and only ifs, which are labeled in the margin. So first, we've already seen in a previous video that the dynamics of z maps to az consists entirely of cycles if and only if that function is bijective. Second, since this function maps the finite set, in particular z mod nz, to itself, bijectivity is actually equivalent to injectivity. I'll remind you again, that's just a general fact about functions from a finite set to itself. Third, the definition, by definition, injectivity is the following statement. It says that ax is congruent to ay mod n implies that x is congruent to y mod n. Okay. Fourth, if we rearrange that statement there, so taking the x and y together into x minus y, then since the x and y appear only in the fixed combination x minus y, which we can call z, this is actually just equivalent to the statement in terms of z, that if az is congruent to 0 mod n, then z is congruent to 0 mod n. Okay. Fifth, by definition, so unraveling the definition of modulus, or modular congruence, this is equivalent to n dividing az implies that n divides z for all z. So I'm going to label this with a star so we can come back to it later. Okay, so we've done all on the screen so far, all of the equivalences 1 through 5, and all we have left is equivalent to 6. Okay, so that means we've got most of it already. But I want to make a little room, so I'm going to remove the stuff that we have here, and I'm going to slide up step 5 to give me a little room to do the rest of the proof. Okay, so what remains to show is that the star is equivalent to GCD A and N being 1. So I'm going to have to do the two directions of this separately, in fact, because they're a little bit more involved. So let's do the backward direction first. So we'll suppose that the GCD of A and N is 1, and we want to show star, so we'll suppose that N divides AZ. Okay, so, but since N and A share no common factors, since they're coprime, this actually implies that N divides Z. So that means that we've proven star. Okay, so that's the one direction, that's the sort of easier direction, but we also have to prove the other direction of the implication. So let's make some room again. I'm just going to use this same spot and prove the other direction. All right, so for the other direction, we want to show that star implies that the GCD of A and N is 1. So we have to assume that star holds. Then it has to hold for any particular Z because it's a statement about all Z. So let's take Z to be equal to N over G, where G is just going to be short form for the GCD of A and N, whatever that may be. We want to show it's 1. We don't know that yet. So by definition, the GCD of A and N has to divide A. So G divides A. Okay, so then N is G times N over G. Okay, and that has to divide A times N over G, simply because G divides A. But that latter thing there is just A times Z. So we have that N divides A times Z. All right, and now we have an example where we can apply star. So by star, that means N has to divide Z itself. Now Z is N over G, so N is dividing N over G. But N over G is generally going to be smaller than N, right? Unless G equals 1. So this is only possible if G equals 1, which is what we wish to show. And we're done. Okay, so there we go. We've shown that the dynamical portrait of Z maps to AZ consists entirely of cycles if and only if A and N are coprime. So this fact is going to be immensely useful if we head further towards number theory and cryptography and various different subjects. But of course, we're very far from answering the full question of what the dynamical portraits look like. How many cycles are there and what size are there? Which elements are in the same cycle as one another? When the function isn't bijective, it looks like there are some cycles and some tails or feeders heading into the cycles. And so what cycles do we get? What elements line the cycles? What elements are in the tails? How many tails are there? And what length are they? So these are fantastic questions, but for another time.